please open your Coq IDE, and if you don't have it on your laptop, just open it on the Coq.js website. So there is this web version. Today we're going to start actually proving stuff with Coq, but I'm not going to dive any deeper into how Coq actually works. So I'm just going to show you how to use Coq for today. Now, if you remember the last session, one of the things that we did in the last session was to write a really huge proof. And this was the proof that I wrote here. And you saw that I had to start from my conclusion and make my way back, basically. So I had a huge proof tree. Now I want to do something similar, but now I want to use Coq to help me. So let's do the very basics. So first of all, when you open the Coq editor, you have 3 parts here. So this is where you write your code. And this part is where you will see what you have to prove. We will see that very soon. So it will show you the sub goals that you have to prove in order to prove the original theorem or lemma that you wanted to prove. And here it gives you just a bunch of messages. So if you write something that doesn't mean anything, like if you have syntactical errors or anything, you will get the messages here. And generally, every command in Coq ends with a dot. So if you're a C or C++ programmer, you're used to putting a semicolon at the end of everything. Here, you just have to put a dot. Okay, so let's start. So in my code, I can have different sections, and you can think of a section basically a function. You can also think of it as a small block of code that is somehow different from the rest of the code. You don't necessarily have to use sections, but you can. So let's just have a section. So I just define section A. I can give whatever name I want, and everything ends with a dot. Now, here's the thing. Coq is an interactive theorem prover. So as you write your code, you can also execute it at the same time. And the way you can execute this one line of code that you've written is by clicking this one, basically the down arrow, which goes forward by one command. Or you can also do control and down arrow. And so here's what happens here. In this case, it was successful. We successfully created a section. Congratulations. So whenever you see the green color, it means that the execution of that part of code was successful. And if I want to end the section, I can just write end A. And basically, the idea here is that any variables that I define inside this section are only accessible in this section and nowhere else in my code. So very much defining scopes for variables. That's all these sections do. Okay. But let's say that I want to prove a very easy theorem. Okay. So let's say I have a variable, and let's say I call this variable P, and it's of type prop, which means proposition. So I just have a propositional variable P. And here's the very first theorem that I want to prove. So this is a theorem, and I'm going to name it my THM. And what this theorem says is that P holds if and only if P holds. Okay, so I'm just showing you how to write a theorem. So you have to give it a name, then you have to write what the theorem is, and everything ends with a dot. Okay, so can you open that door, please? Now here's the thing. As soon as I execute this line of code, and you see that this is now green again, so I immediately get a goal on this side. So this is what I have to prove. I have to prove to Coq that P if and only if P, right? And these are basically written like the proof rules that we saw in the previous session. So I have to prove this. And currently I have only one goal, and my only goal is to prove this. Now, let's look at my assumptions and let's look at my goal. So the goal is to, of course, prove P if and only if P, but I have one assumption. And this assumption is that P is a proposition. So that's how we read this assumption. It doesn't mean that P holds. It just means that P is an object of type proposition. Okay. So I have to prove this. So we usually start with the word proof on one line for itself to start a proof. Okay. How would you suggest I prove this? Okay. Basically, I have to create a proof tree, but I don't want to create the proof tree myself. I want to kind of guide Coq into the right direction so that Coq can find the proof, right? So I don't want to create a tree like that as before. So instead, what we have are called a bunch of tactics. And each tactic is basically one level of reasoning. You can think of it like that. So a tactic basically takes my current goal and converts it to some other goals. And of course, those goals have to be equivalent to the original one, so that I continue this until I get a bunch of goals that are trivial, and then I'm done with the proof. Okay? So one of the first tactics that we have is called actually split. So I can write split here and look at this part here and see what happens when I do split. Okay. So basically, this was an if and only if, right? And when I'm doing split, it's splitting it into two different sub-goals. I have to first prove one side of the implication and then the other side. I mean, in this case, both sides are basically the same. So now I have two goals that are the same. Okay, now I have to continue with proving the first one. So I want to prove P implies P. Okay. Now, what I can do at this point is that I can take this first P and I can put it up here in the assumptions, right? Because this is an implication. Now, the tactic that does that is called intro. So if I do intro, as you see here, it just took the P, put it up here as an assumption, and it also gave it a name. So this assumption is now called H. Okay. And so I have an assumption P, I have to prove P. I have what I want to prove as an assumption, so I can just write assumption, which basically tells Coq that at this point, what I want to prove is already in my assumptions. And I do this, and as you see, as soon as I executed this assumption, the first goal is achieved. So the first goal is removed, and now I have to do my second goal. So I have to prove the second part. But of course, the second part is proven exactly in the same way. So I can repeat the same proof, or later on, I'll show you how you can avoid repetitions. But anyway, so I can do intro, which puts the P up there, and then I can do assumption. And that's it. So it says no more goals. I proved everything that I claimed. I claimed the very trivial theorem, and I gave a proof for it. So at the end of every proof, you have to write QED. And if QED passes, it means that you have really proven everything that you have claimed. Okay, so in the homeworks of this course, I generally give you a theorem, and you have to write a proof, and you have to pass QED. Okay. Now, I have this theorem. So here's what I can do. I've given it a name. It's called my THM. I can first write check my THM. Oops, sorry, with capital C. And it shows me what my THM is. But I can also say print my THM. And this one is actually the proof tree of how this whole thing worked. But this is not very human readable. So we don't really care about proof trees in general. But the important point here is that I just guided the proof assistant to a proof. And then the proof assistant could find a formal proof, something that looked like that tree that I drew for you last session. And then it could also verify that proof. So all of those things must happen for QED to pass. Okay, but this was a very simple example, and I can also end my section, and I always forget that these are capital letters. Okay, this was our very first proof, and you saw already 3 different tactics. So one tactic is split, one is intro, which basically says that if you want to prove an implication, you can take the left-hand side of the implication and put it in your assumptions. And then the other one was literally called assumption. It's when you want to prove something that is already in your assumptions. Okay. Let's open a new section. And let me see. Let's say now I have 2 variables. So I have 2 variables, P and Q. I have to write variables here. And they're both propositions. And as you see, as I execute this in the messages, it just says that P and Q are declared. Okay, now I want to prove this theorem. So I'm just going to call it theorem 2. I want to prove this. Okay, P entails Q entails P. Okay, and by the way, when I don't put parentheses, this is what I mean. Okay, so I give it this theorem, and again, you see that I have one goal now, which is to prove this, and the only assumption that I have is that P and Q are propositions. Again, I have to repeat this many times. This does not mean that I'm assuming P is true or Q is true. It just means that I'm assuming P and Q are of the type prop. So it's just the type of P and Q, they're propositions. Okay. So let's start the proof. How would you prove this? First split. Well, there's nothing to split here. So if I say split, it just gives me an error. So previously I could do split because it was an if and only if, and then I could say split the proof into 2 parts. First prove one side of the implication and then prove the other side. Okay, but which one of the 3 tactics that we've seen can be applied here? Yeah, so I can just do intro, right? So I do intro, and P is now one of my assumptions. Now, again, I can do intro. And now Q is one of my assumptions. And now I just need to prove this, but as you can see, I have to prove P, but P is already in my assumptions. So I can just say assumption at this point. And that's it. This is a proof. And I have no more goals, so I can just write QED and QED passes. By the way, if my proof is not finished and I write QED, you see that I get an error like this. And if this happens in your homeworks, you get 0 points. Okay. But there are also some shorthands. For example, let's say I'm here, let's say I'm at the beginning of my proof. Instead of writing intro several times, I can just write intros. And it just does intro as many times as it can. Right. And then here again, I can just write assumption and QED. And B. Actually, I don't want to end my section. Let it be there. Okay. Let me give you an exercise now, and I want you to do it right now in your Coq IDE. So let's say that, okay, actually, let me end this section because I don't want to use it so that you can just type everything in. So you can just type starting from here. Let's say I have a new section C and I have variables P, Q, and R, and they're all propositions. Okay, and this is a theorem. I'm going to call it exercise 1. And this is what my theorem says. P entails Q entails Q entails R entails P entails R. Oops, I forgot that these were lowercase. Okay, let's make them uppercase. Okay. So this is what I want you to prove. Okay. So I'm going to actually use a new rule here as well, a new tactic. But it was nice having you try. Okay, so here I can basically only apply intro, right? So I can just write intros and it applies intro as many times as necessary, or as many times as possible, but I want you to just see what happens every step. So if I apply intro once, the left-hand side of the implication goes up here. And then if I apply it again, the left-hand side goes up. And now I apply it again, and the left-hand side goes up. Okay. So what is the problem here? These are my assumptions. I have the assumption P implies Q, Q implies R, and I also have P, and I want to prove R. This looks very obvious, right? Because, well, P implies Q and Q implies R, and I already have P, right? So what should I do here? If I wanted to do a normal proof, how would I go on with this? Yeah, so I kind of need a lemma, right? I need to say that Q holds, right? So how can I do that? So I can write assert Q, okay? And this means that I want to prove Q, and then I want to just prove this as a lemma, and then I want to use it in the proof of R later on. So when I say assert Q, it says, okay, now prove Q. Okay, how am I going to prove Q? I have P, I have P implies Q. So if I put H and H1 together, I should get Q. But this is what we call modus ponens, right? So for this, actually, when it's this simple, I can just write auto. Okay? And at this point, it understands. It understands that if you have P and P implies Q, you have Q. So just writing auto figures that part out. But now here, I have P, I have Q. But again, I have Q and I have Q implies R, and I want to prove R. So again, I can just write auto. And that's it. No. Yeah. And I can do QED, and that's it. So the only thing I wanted to show you here was basically this concept of assert. But then we also have auto. But now this is the part where you will be really angry at me. This whole thing is a tautology, right? It always holds. So we have another thing called tauto, which basically checks for tautologies. And in this case, I said this is a tautology, and tauto checked that. And so, yeah, that's my proof. That also in previous section. Yes, but I wanted to teach you about all the other cool stuff. Okay, so, but let's not use tauto at all. And let's see how we can prove things without auto. So first of all, we applied intro several times, so it's better to just write intros. And when we are here, again, the lemma that I wanted to prove, the thing that I wanted to assert at this point was that Q holds. And then I could prove this with auto. And then now that I've proven that Q holds, you see that Q is added here as an extra assumption that I can now use for my proof of R. And now the proof of R is also automatic, it's just auto. Okay. Should I give you another one? Here's another one, exercise 2. This should now be super easy based on what we already did. Do this, P, P, Q, P, Q. Now, the point that I want you to really see here is that these exercises are trivial. We can easily do them, but if you had to manually reason about this, you don't really have a good intuition what this sentence is saying, right? Like, if P implies that P implies Q, then that implies that P on its own implies Q. So this is something that is not that easy to wrap your mind around as a human, but if you just follow these rules and tactics, you can easily prove it in a theorem prover like Cook. Okay, so prove this one. Let's just do intros. And this is what we get. So at this point, you can just do auto, right? Because what auto does is that it applies basic reasoning techniques, especially like modus ponens, as many times as it can. So if I apply modus ponens once, what happens here is that I have P, and I also have that P implies this. So I get that thing, I get P then Q. So if I don't want to use auto, actually, I can do this. I can assert that P implies Q, okay? And then I can do auto on this one. And now, as you see, I have P implies Q. But now I have P and I have P implies Q, so I have Q. But again, even without this assert, as we saw, like at this step, auto is just fast enough that it knows what to do. Okay. Great. Let's do some more interesting stuff. Let me see what I have here. Okay, this is basically a variant of what we already had. But let's go over this one as well, because this one actually has apply as well. Okay, so I define some variables. This is the theorem that I want to prove. I do intros, and oh, okay, so this is the answer to your question that I didn't remember. If I don't want to do auto, if I want to do it one step at a time, I can use apply. So basically, the idea here is that I want to prove R, okay? And I have R on the right-hand side of H0. So what happens if I apply the rule H0, if I apply the assumption H0? It basically means that now I have to prove Q, right? Because if I want to apply H0 to prove R, H0 gives me R, but that only works if I have already proven Q. So as soon as I apply H0, you see that it asks me to prove Q now. Okay? Okay, now I want to prove Q. But I have this H that has Q on its right-hand side, so I can say I apply H. But in order to apply H to prove Q, I have to now prove P. but P is already an assumption, right? So I can just use assumption and that's it. Actually, Ahmed, this is not exactly what you asked. This is like the backwards version of what you asked. Because if you look at it again, so I did intros and this is the state I'm in. These are my assumptions and I want to prove R. And I say basically that the last step in my proof of R is going to be the application of H0. That's what I mean by apply H0. So when I do apply H0, what I'm saying is that I can prove everything that H0 needs. I can prove the left-hand side of H0, and then I can apply H0 and R would be proven. So when I write apply H0, then it asks me to prove the left-hand side of H0, which is Q in this case. Now, in order to prove Q, again, I say apply H, and it will ask me to prove the left-hand side of H, which is P. And then this P is already an assumption. So that's good. Okay, so until this point, we've seen assumption, intros, apply, auto. Let's do something else. I'm going to copy this here because I don't want you to cheat. So let's say I create a new section. What was my previous section's name? I want to end it and see. Okay, I have a new section and here I have new variables P, Q, and R. Now I have a hypothesis, H. And this is my hypothesis. And now I want to prove a lemma. A lemma and a theorem are basically the same things. So you can write lemma, theorem, corollary. Koch doesn't care about these things. No matter which one of these you write, you have to give a proof. So I have this lemma L now. And by the way, this is how we write and. This is P and Q.
Oh,
okay.
One character or two characters?
Yeah, it's with 2 characters. So this is how we write and. This is how we write or. Okay, you will get used to this. So I have 3 propositions, P, Q, and R. Not is just the tilt. Yeah. Okay, so I have P, Q, and R. And my hypothesis is this. P implies Q implies R. And using this hypothesis, and I've given it a name, I could give it any other name. I could give it the name HY, whatever. I want to prove this lemma L, which says that P and Q implies R. And as you see, when I do this, here in the goals panel, I have one goal, and the goal is to prove the lemma, but I can use the hypothesis, right? And I can, of course, use the fact that P, Q, and R are propositions if I ever need that. Okay. How should I prove this? So tell me which tactic to use now. First, I don't think we can split, no. So split is basically applied whenever you have to prove 2 things and you want to say, I prove each one of them separately. Yeah. So here we can apply intros. Right? So let's apply intros and let's see. Okay. So I have P and Q. And I also have the hypothesis that says P entails Q entails R. And I want to prove R. Now, again, at this point, if you write auto, no, it's not smart enough. Okay, thank God. It's not smart enough to just do this automatically, but probably Toto is smart enough, yes. But okay, let's not do that. Let's actually give a proof ourselves.
Can we split H into 2 things, P and Q, separately?
Yes, so that's what we call destruct. So we can write destruct H. And here's what it happens. H was P and Q. So you now get two different hypotheses. One is P, one is Q. Okay, what next? Okay, this is very similar to one of the previous ones. So what would you do at this point? Apart from auto, again, auto will probably work. But let's say we don't want to do auto.
We assert Q home.
Yes, so we have to apply, but which one? We have to apply HY, the hypothesis. Right? So I want to prove R, and R is on the right-hand side of HY. So I can just say apply HY. And you see, here's what it tells me. It tells me in order to apply HY, now you have to prove to me P and Q.
Assumption.
Yeah, but both P and Q are assumptions. So I can just, for P, I can write assumption, and for Q, I can also write assumption. And that's it.
Can we write assumptions instead of two assumptions?
No, but what you can do is that you can use a semicolon, because basically when you're applying this hypothesis, you're getting two goals. So you have to have that tree notion of the proof in your mind. So your tree has branched, and now on one branch you have to prove P, and on the other branch you have to prove Q. But if you want to use assumption on both branches, you can just use a semicolon and write assumption, and then it will apply assumption on both branches. And in this case, it succeeds. Okay. Let's see if I had. Yeah, so I have kind of a different proof here. So let's go through this. So again, it's exactly the same lemma as before. So first we're doing intro. So we're taking P and Q and putting it into our assumptions. And then at this point, before destructing H0, we're applying H. So if I apply H, I have to prove P and I have to prove Q. But I have P and Q. So I destruct H0 so that I have both P and Q. And now I say my assumption, I have the assumption P, so it's assumption. But look at this. So at any given point, you're only seeing the assumptions that you have in the current point of your proof tree. Okay, so here's again this proof. So we start at the beginning, we do intro, P and Q goes up there in the assumptions. And when I apply H, I have to prove two things. I have to prove P and I have to prove Q. But I have to prove both of them with this set of assumptions. But then when I do destruct H0, I'm doing it only in the part of the tree that is for the proof of P. Okay, so you see I have this H0, which was P and Q, and I destruct it. And then I use assumption to prove P. But as soon as P is proven and I'm moving in my tree back to proving Q, I again have the H0 that I destructed before. So it just keeps track of what your assumptions are at every node of your proof tree, which is quite great. So I have to destruct H0 again and use assumption again, and that's it. Okay. Yeah, let's do this. Let's end this one. Let's start a new section. What happens if I actually use quantifiers? So let me first do a very simple example. So let's say I have a variable P, which is a proposition. And this is my theorem 1, which basically says P if and only if P, or P implies P, right? I can prove this, and the proof is actually quite easy. Again, just like before, you do intro and you do assumption. Or you could just do auto or toto, or whatever, it will work. Okay. So I have this simple theorem, but now suppose that I want to use this theorem in another theorem. So for example, let's say this is my second theorem. Okay. So I can, of course, prove this theorem on its own. And this is not that hard because, I mean, it's a small one. So we can just do it. Yeah, let's just do intros. And then you see that we just need assumption after that. Right? So it was actually quite easy to prove this theorem on its own. But ideally, I want to be able to use the proof of my previous theorem. Right? Because previously I'm showing that P implies P. And if I just replace P itself here with P implies P, I get this other theorem. Right? But to do that, I will probably need something a little bit stronger. So here's the thing. Instead of just saying that P is a variable, I'm going to say my first theorem is going to give me for all P that is a proposition. So as long as my P is a proposition, P implies P. So I write my theorem like this. And now I want to prove this new theorem. So the only difference is that now I have a quantifier. I want to say that, you can see my quantifier here as well. I want to say that for all P, as long as P is a proposition, of course, P implies P. Okay. So what would you do if you want to prove a for all statement normally? All I want to show you here is that this is very intuitive. So how do you prove a for all statement? Basically, if I wanted to prove this, I would just take this part, which says that P is a proposition, and I would put it as an assumption. And then using that assumption, I would try to prove this one. Right? So let's see. Let's see what happens if I write the, what should I write? Split, intros. Oh, okay, yeah. In this case, I can also write intro. So if I just write intro, you see that it takes this part, which was basically the assumption in the for all, and puts it up here in my assumptions, and then I have to prove this part. So say this again, I apply intro, and now this is what I have to prove. But again, for this one, I can apply intro, and then I can apply assumption. Okay. So now I have a theorem that has a quantifier in it. It says for all P, for all propositions P, I have this. So let me actually change this name. Let's do it something like this, and let's say I have a variable. Actually, let's have variables Q and R, which are both propositions. And let's do this. Okay. Now, again, I can just write a simple proof, or I can try to use the proof of T1. Okay. Now, the way I can use T1 in T2, since I've already proven T1, is that I can just write this, pose proof T1. Okay. And as you see, this just added T1 to my list of assumptions. Because what I'm saying here is that I've already proven T1. Give me T1 as an assumption so that I can write a proof for this T2. Okay. What should I do now?
We should replace Q implies R as T1.
Yes, so I want to take H and I want to replace this quantified variable P with this expression, Q implies R. Okay, so we have that as well. It's called specialize. So I can just write specialize H with, and here I say what I want to put for P. So I say P becomes Q implies R. Okay. So all this is saying is that this was a universal quantification I was doing for all. So I can put whatever I want in place of P, as long as it has the right type, of course. It has to be a proposition, right? So all I'm saying here is that instead of P in this expression H, wherever you see P, put this expression, Q implies R. And I do that, and as you see, my H changed. And this is now the format of H. Okay, what do I do now? No, why apply H?
Assumption.
Yeah, this is just the assumption. Yeah, and that's it. So that's how you use the proof of one theorem in another theorem. Okay. It's good. What else? Let me see what other examples I have here. Okay, this is basically the same example. Okay, I just want to do one more example with propositional logic, maybe. What happens if I want to prove OR? So let's have a simple theorem like this. Let's say that I want to prove that P implies P or Q. Okay, pretty easy. Oh, I have not defined P before. Okay, variable P. Okay, so I want to prove this. So I just want to show you the typical way that we prove an OR. So again, I can do intro. P goes up there. So I have P, but I want to prove P or Q. Okay. Again, I can cheat. I can just write auto, or I can write tauto for tautologies, and it just figures it out. But the other thing that I can do is that whenever I'm proving a disjunction, I can basically say that I want to choose to prove the left-hand side or the right-hand side. Okay, so I can just write left, which means I want to prove the left side of the disjunction. And so it just erases the right side. It says, okay, prove the left side for me. So here's how it looked like before. But then when I do left, it just removes the right-hand side, and I just have to prove the left-hand side. Okay, and now the left-hand side is just an assumption. Okay. Let me see if I can find another nice example. Okay, so since we have only 5 minutes remaining, let's do this. This is actually an example from the cookbook. So what's the name of the section on here? So and D. Let's start a new section E. And let's say the variables I have are P, Q, R, S, and T, and they're all propositions. And this is the lemma, and it's called the diamond lemma. So this is what I want you to prove. You can see it up here.
Oh,
Yeah.
QRTPT, that looks like a diamond. Yeah.
Okay, and again, just to show you that this is possible, like if it's a tautology, Coq can find it on its own. But again, I want you to actually write the proof for this one. Yeah, so in this case, we will have to apply intro many times. So let's just write intros. And this is what happens if you write intros. So it applies intro as many times as it can. And now you have this. Okay. So it's again kind of obvious what we should do. We want to prove T. And the only assumption that has T on its right-hand side is H1. Right? So let's just try that. Let's say apply H1. So now instead of T, I have to prove Q and R. Okay, I want to prove Q, apply H, yes. Now I have to prove P, it's an assumption. Now I have to prove R, apply H0. Now I have to again prove P, again, this is an assumption. And that's it. So as you see, in many cases, it's actually quite obvious what rule you have to apply. And this is actually what Otto is doing. So Otto and actually, well, not Otto, but Toto is basically following simple rules of propositional logic and figuring out whether what you've given it is a tautology or not. Okay. Great. So let's have lunch and let's come back after lunch for some first order logic. These next examples are actually coming from a course of Andrzej Bauer of the University of Ljubljana, so I'm giving credit to him. But let's prove some theorems that actually have quantifiers in them. And let's see how we can do that. Let me minimize this one. Okay. So first of all, let me just start a new section. I don't know what to call these sections, whatever. Okay. So one of the things that we know from basic logic, but doesn't exist in intuitionistic logic, is this law of excluded middle. So I can have a definition of this excluded middle. And basically what it says is that for any proposition P, either P holds or not P holds. Okay. So if I want to write this, how can I write it? Well, I can just say for all P of type proposition, P or not P. Okay. So that's it. So I just defined this, and this is, by the way, I think the first time we're using the keyword definition. So I'm just giving a name to this entire expression. So whenever I say excluded middle, what I mean is this entire expression. Okay. And there's also another law in logic, which is, I think, equivalent to this, and this is called Peirce's law. So I'm just going to call it Peirce. And this is how it goes. It says that for every two variables P and Q that are propositions, suppose that P entails Q entails P entails P. Okay, hopefully I wrote this correctly. Yeah, this is called Peirce's law. Okay, you can kind of check that both of these definitely hold. So if you just look at this in propositional logic, well, either P is true, in which case this is true, and if P is false, then not P is true. So in any case, this entire expression would evaluate to true. And here you can do something similar. You can just try all the possible combinations of true and false for P and Q, right? So for example, if P is true and Q is false, then this part is false, which means that this part is true, which means the entire thing is true. Okay. But a very important point is that actually, oh, someone is trying to join. Yeah. Coq never does that. So Coq never draws tables of true and false and check all the evaluations. So we don't have something like excluded middle in Coq on its own. But let's try to prove a theorem. Let's try to prove, I'm going to call this one EQV because it's an equivalence theorem. I want to say that excluded middle holds if and only if Peirce holds. Okay. Sorry, I should have just put a dot there. Okay. So now, as you see, this is my goal. I have to prove this. How would you suggest I start my proof? Sure, we can do split, but even before that, I want to really replace these names with their actual definitions. Right. So this is called unfolding, and I can write unfold excluded middle. Ooh, typo. Okay. So, and as you see, it just replaced excluded middle with its definition. And now I can do the same thing for Peirce. I can say unfold Peirce. I could also just write one line that said unfold both of them, but whatever. Now they're both unfolded. So now the first step would be split, because I want to prove an if and only if statement, and well, I have to prove both sides, and hopefully I want to do each side separately. Right? So let's do a split. Okay. So at this point, I want to give it back to you guys to prove it. So prove this entire thing. Write everything that I've written from the beginning of section 2, get to this split, and then complete the proof. Okay, so let me tell you about another one of these tactics that might make your life a little bit easier. You can write first order, and it basically applies as much as it can basic rules from first order logic. So I can do this even before that, so I can just do first order. It simplifies a lot of things. Okay, but you should be able to solve this even without first order. But with first order, you get this one, which is supposed to be easier to solve. Okay, so let's see what we have here. This is the state where I asked you to continue. So I've already done the split. Now I want to prove this first goal. Okay, so this is an implication. And since it's an implication, it actually makes sense to just do what was it? Intro. Yeah. Okay, so I do intro, and this takes the left-hand side of the implication up here in my assumptions. Okay, and now again, I have for all PQ that are propositions, something. So this is also kind of like an implication, because I'm saying that if P and Q are propositions, then I have this, right? So I can actually do intro again. And by the way, you can just write intros and it will do intro as many times as it can. But I want to do it step by step. So I do intro again. And as you see, it took P out. And I do intro one more time and it takes Q out. So this is what I have now. I know that P and Q are propositions. I have an assumption that for all P, that is a proposition, either P holds or not P holds. And I have to prove this. But this is again an entailment. So I can again do intro. And now this is what I have to prove. I have to just prove P. Okay. So actually a lot of you had gotten to this point too, which is nice. But now here's the problem. If I want to prove P, I want to probably apply the rule H0, right? Because that's the only rule, the only assumption I have here that has P on its right hand side. But if I want to apply H0, I have to then do something about Q. I don't know anything about Q. I just know that P entails Q, but I don't have any information about Q. So what really gets almost everyone stuck here is that we need some information about Q. So how can I get some information about Q? What do I know about Q if I have all of these assumptions? So this one is definitely not going to give me anything new about Q, right? And this one is just telling me about the types. So P and Q are both propositions. But this one, this is not talking about a single P. This is talking about any P. So it's saying for all P that is a proposition, we have P or not P. So I can plug in Q here and see what happens, right? So how do I plug in Q? I can do specialize. I can say specialize H with P equal to Q. So I'm putting Q in place of P. Okay. And let's see what I get here. Okay. Now this is better. So I don't have any more quantification. I can think of this more naturally. Okay, at this point, I can go, this is a tautology, but it fails. It doesn't find the tautology. Okay. So what else can I do? I want to prove P. Well, I know that either Q holds or not Q holds, right? So I can actually split my proof based, and now as you see, first it says, okay, first for the case that Q holds, prove P, and then I have to prove P for the case that Q doesn't hold. Okay, so my assumption was Q or not Q after H, which means that I'm first proving the same thing P, only having Q in my assumptions, and then I'm proving P only having Q in my assumption. So this is before the destruction of H. This is after the destruction of H. Before, after. Okay. So now I have Q and I have to prove this one. So I have to prove P. I know H0 as well. So I can now say apply H0. Okay. But when I apply H0, I applied H0 to prove P. So now I have to prove P entails Q. Okay. Now what? Apply H again Would this work? No.
Oh.
Because the problem is that there is no premise here. It's just Q. Right?
No. We specialize H with P and then control.
No, but well, if I know that Q holds, then P implies Q definitely holds as well, no matter what P is.
Assumption.
Right? Yeah, well, not assumption, but I can do auto. Or I could also do auto. Okay. Now it gives me the other side. And the other side is when I have not Q in my assumptions. I have to prove P and I have not Q. What should I do here? Again, let's apply H0. Okay. But now it says P implies Q. But that's also fine, right? Because if I have not Q in my assumptions, that means that, well, Q is false, right? Oh, okay, this is not good. Can I prove this? No. If I have not Q and
If Q is false, then P should be definitely be true.
yes. But the point here is that since Q is false, okay, so let's just do a manual analysis of what's happening here. What happens if P were true? If P were true, this one would be false, right? And false entails P. Yeah. But what if P were false? Then this is false, and then
true. No, the first side is true. False implies anything is true. True implies false is false. According to your truth table, P should only be true.
Yeah. So the problem we have here is that we need to also know something about P. We can't just say we know something about Q here, right? So yes, but I've already destructed H. So let's go back here and let's delete this and let's see what we can do from here again. So I want to do basically casework. I want to take the case where I want to do a casework on P and I want to also do a casework on Q. There has to be an easier way for this. I feel like we're doing too much work, but okay, let's do this. So I can say assert G to be H of Q, which means basically put Q in place of P. The difference with specialize is that this one just adds it, and I still have H. Okay, whereas when I was doing specialize, I lost H itself.
So this one just adding a new assumption without deleting the original.
Yes. So this is like adding a specialization of the original one, but also keeping the original one. And now I can say specialize H with P in place of P. Okay. And now I have all of these things. Okay, at this point, I think I can just say auto and it will work. No, it doesn't. Auto, yes, auto works. Okay, so basically the idea was that if you do a casework over both P and Q, then it becomes a tautology in propositional logic. And then you can just write tauto and it works. But let's not use tauto, let's actually torture ourselves. So how would you solve this now? Do you want to first do a casework on Q or on P? You can see my screen again. So let's go back to the place where we did the specialization. So now we have the ability to do casework on both P and Q. So from this point, it should be easy to finish the proof. So let's do it on P first, destruct H. And then this one is just an assumption. And for this one, let's say destruct G. So okay, now we have to prove this one. How do you prove this one? What does it mean to prove this one? So in my assumptions, I have not P, but I want to prove P. What does this mean? What do I want to get?
Oh, we want to prove Q. We should prove Q. We should apply H0 and then we show Q is true.
No, that's not the point. The point is that here I have to show that there is a contradiction in my assumptions. Right? Because if my assumptions have no contradiction in them, then I have not P here and I cannot get P here. Okay, let's see, can Toto solve this? Yes. So there is definitely a contradiction in the assumptions. Okay, but let's just go on as normal and see what happens. So I want to prove P, I can apply H0. Okay, now I have to prove P implies Q. Okay.
In the first case, we already have H1.
Yeah, but I have not P, so I know that, yeah, okay. We already have Q here, and if I want to prove P implies Q, that shouldn't be a problem because I have Q. Right, so this one is just auto. Since I already have Q, I also have P implies Q, okay. So now we're going to the other case, and this is the case where I had not P and not Q. Okay, what do I do here? Again, I do the same thing, right? Apply H0. And here again, because I have not P, P implies Q is always true, so I can just do auto. Now I can do Toto. Yeah. Okay, we proved one side. Now we have to prove the other side. So what we proved until this point is that if we have excluded middle, then we also have Peirce's law. Now we want to prove that if we have Peirce's law, we also have excluded middle. Let's do this. So I'm just going to do intro, but I'm going to do intro many times. So I'm just going to write intros. So this is what we have to prove. We want to prove P or not P. And this is what we have. So what would you do here?
Specialize.
Okay, specialize H. What do you want to put for P and what do you want to put for Q? Which one do you want to change?
Change Q for to P.
Change Q to P?
It's P or not P as oh.
Okay, Q becomes P or not P. I'm just following what you're saying.
No.
Sorry, specialize H with
P. Sorry, P equals to that.
Are you sure?
Because we want because Q is not P.
Okay. So now because we had a P inside H and we had a P outside of H, Coke understands that these are not the same P. So one of them became P0.
Oh.
Okay, what do you do now?
is that I can specialize P as P or not, and itself P was.
Okay. Specialize H0 with P0, also P or not P. Oh, sorry, it's called H. So with P0, no such bound variable. What? Oh, but we should be able to specialize it again. This is H. I should be able to put something for P0, right? Specialize H with P0Q. Okay. P0P. No such. I don't know what's happening here. Okay, maybe let's go up and let's not do that one. Can you find a better specialization?
Can I try one just P state P and Q be not P?
Okay, so you want Q to be not P?
Yeah, and P is like.
Okay. And P remains P. I don't know the syntax for this. Okay. Specialize H with P. It's P. Yeah. Okay. So P remains P and Q was replaced with not P. What would you do from here?
We apply. No.
We cannot apply H. In order to apply H, what we want to prove should be the right-hand side of H. Right? But the right-hand side of H is just P.
Maybe also this time.
Okay, let's go back to here before our specializations. What else can we do other than specialize here?
Assert?
No, well, I want to prove a disjunction, right? I want to prove an OR. So I can just decide to prove the left-hand side or the right-hand side.
For left-hand side.
Right?
Left-hand side. It's obvious.
Is there something obvious here?
I think if we choose the other side, then we can just modify how we visualize it and then it works out. The point that.
Okay, so you want to again specialize H?
Yeah, we just.
With Q, not P. And specialize it again with P0P. PP. Okay. Now, do you want to prove the left-hand side or the right-hand side? Because we have a disjunction here.
Oops, that right-hand side. Okay, left-hand side is obvious because we can apply H.
Okay, but it's enough to prove one of them. So if I can just prove the left-hand side, I would be done. But I don't think I can prove the left-hand side. So here's what happens if I apply H.
Oh, yeah.
Okay. Now what? Now we can do intro. Put it up there. Now I have to prove P. So I can again apply H.
Intros rather than intro.
Okay. Again, intro. Do you see what's happening here?
Let's try the last
Oh,
time.
endless loop. Endless loop.
Yeah. Okay. So this idea of specialize is actually correct, but you have to figure out how to specialize.
But why can't we use auto? Because the result is automatically true, no matter how the assumption.
If you remove too much.
No, you see, auto doesn't work here.
Okay.
And auto actually does work. But it only works for the first one, which we already had. I can just write first order to simplify it a bit. So this is what you have to solve.
I think we can do the same thing as before, but we do that right?
Okay,
And then
so
eventually check the-
you want to say right? So at this point, you want to just prove the right side?
Yeah,
Okay, right.
Same way, like Q not P.
Okay, specialize H with Q not P. And specialize it again with PP. Ah, I need a space there. Okay, now what?
Look
And
even
now-
more complicated.
We assume that the conclusion is not true, that P is true.
So you think this is a tautology? No, it's not.
Why total doesn't work this time? Yes, it is that end. That end.
And auto just doesn't do anything. So tauto fails and auto doesn't do anything.
Okay.
Okay, let's go all the way back again. And let's also apply first order so that it simplifies it as much as possible. So just write this and continue from here and try to finish the proof.
So how did we do that third thing where we specialize without throwing away the hypothesis?
It was assert.
Yeah, like what was this?
Okay, so I can do something like this. I can say assert G, which is H of Q, let's say. So the idea of specializing and putting something in place of Q is actually correct, but you have to put something more clever in place of Q. You can't just replace Q with not P.
Are we specialize Q with a false, directly false?
Yes, but that would not work either.
Not working either, because if we specialize Q with false, then P implies Q is exactly P. And then P,
I think this would probably work for the first part, not for the second part. And I mean, we could already solve the first part with a lot of effort, right? So we can solve the first part by doing casework over both P and Q. The second part is the hard one. So let me actually change this theorem, write it in the other way around so that the hard part comes first. So Pierce, if and only if excluded middle. Okay, and I'm going to unfold Pierce and excluded middle. And then I'm going to say split so that I prove each part separately. This is what we want to prove. We want to prove that Peirce's law holds if and only if excluded middle holds. So we first unfold. Then because it's an if and only if we split. Now I want to prove this one and it's an entailment, so I do intros. Now the only really interesting part here is the specialization in H. Yes. So what you put in place of Q is actually this, not of P or not P. Okay. And the reason for this intuitively is that you want Q to be false. Right? So you do this, and as soon as you specialize it, you get this. Okay? And now you can apply the H, basically. So, but what does it mean to apply H here? So look at this. This is the part we had before. Then I'm saying specialize H and put this expression in place of Q. Okay? So this is what I've done. Now I have a new H after the replacement. Now I want to say apply H. How can I apply H? So here's the thing. In H, on the right-hand side, I have P0. Right? And in order to apply H on the right-hand side, I need to have P or not P. So basically, when I say apply H, it means that first put this expression in place of P0, because you can do that because this holds for all P0. And then apply it. So instead of this, I could first write specialize H with putting P to be P or not P. Okay, so I could first have this expanded H, and then I could say apply H. Okay, and now after I apply H, Toto works. Okay, so basically you needed two replacements, but the replacements that you needed were these two. Instead of Q, you had to put not P or not P, and instead of P, you had to just put P or not P. Okay. Now, why did I give you this example? Why did I waste so much of your time? Because I enjoy that, first of all, and secondly, this shows you that it's not easy to find proofs. And you can now understand why Coq cannot prove these things on its own. Because it's, even if you have only a few rules, you can apply the same rule with many different parameters. You can, when you're doing specialize, you could replace this Q with any expression. And you don't know which expression actually works. And again, it's not trivial to find this. So anyway, you don't need to write this second one. You can directly say apply H, because basically what's happening here is kind of a pattern matching. It's that in order to apply H, I need the right-hand side to have this format. Does this have that format? Yes, because P0 is supposed to be a proposition, and this is for all propositions, so I can put P or not P in place of P0. So I didn't need to write the second specialize. I could just directly write the apply and then get the tautology. Okay, now the second part. The second part is actually the part that we could already solve with the casework on P and Q, but let's do it with just one casework. So we first do first order, which basically just applies all of these other simplification rules that we had. And this is what we have to prove. So how do you prove this? Well, here the only problem I have is that I have this extra quantifier in H that I don't like. Right? Because if I just have P or not P, then I can do a casework on P, and that's all I need here. I just need a casework on P. Okay, so I just say specialize H with putting P in place of P, which is just basically saying get rid of this for all P and instead just put this P. Okay, now this is what I have. Okay, now I'm going to do the casework, and whenever I say I'm doing casework, it's basically destructing a disjunction. So I have this disjunction here. I can destruct it, which means that I first prove the entire goal only using P, and then I prove it using not P. So destruct H. So in this case, in my assumptions, I have P, and I want to also prove P. So the proof is just assumption. In this case, my assumptions are just contradictory. So I think I can even write contradiction and it would work. No, it doesn't work. Okay. But again, it's a tautology at least. So I can write tauto and QED and ante. Okay. Let's do another example. But I promise you this example is not going to be as hard as the previous one. Actually, let me just copy it from here before you can see the proof. So this is an example of a theorem that has a bunch of parameters. And that's why I like it. So this is the theorem of Frobenius. So the way we read this is that this theorem has these parameters. So let's say that A is a set and P is a function that maps each element of A to a proposition. And Q is a proposition. Okay. So you can think of this as P being some sort of parametric sentence that talks about different elements of A. So for every element of A, it says some proposition. Okay, so here's what we want to prove. We want to prove that these two things are equivalent. The first one is that there is an X in the set A such that Q and P of X. Okay, so Q was not parametric, it didn't take any parameters, but P was a function. So I want to say that there is an element X in A such that Q and P of X holds, if and only if Q holds, and there is an element in A such that P holds. Okay, pretty intuitive what we're doing here. But can you prove this? So what's the first step you would do? Yes, we have to first split it. So now let's prove the first part, and this is an implication, so it makes sense to do intros. So I did intros. This is what I have now. I have all these things, but I want to also prove this. I want to prove that Q and exists an X such that P of X. Okay, this is a conjunction. Whenever you want to prove a conjunction, you can again do split. So this basically means that I first prove Q, and then I come back and I prove this second part. Okay, so split. Okay, now it says prove Q. What do I know? I know that there is some X in A such that Q and P of X. And I want to just prove Q. Yeah. So what should I say about H? You want to write apply H?
Oh. I think in H that there exists an X in A such that both P and Q hold.
Yeah, but I cannot say apply. What's the name of the command that I should use? I can use destruct H.
Destruct, yeah.
Okay, so when I do destruct H, look what happens here. So this was existentially quantified. So H used to say that there exists an X such that these other things, such that Q and P of X. Now, when I do destruct H, X itself is added here. And of course, X was in A. So all this says is that X is of type A, X is in the set A. And here now I have Q and P of X. But I just need Q, right? So at this point, again, I can probably do auto. No, I can do total. Yeah. Okay. But anyway, if I wanted to be very specific about this, I could then say destruct H again. And now I have Q here and I have to prove Q. So it's just an assumption. Okay. How about the second part? One of my assumptions is that there is an X in A such that Q and P of X. But I just want to say that there is an X in A such that P of X. So I just don't need the Q. Yes, so I do destruct H. And here's the thing. So it again renames this one to X0 because this X is not the same as this X. But if you want to prove an existential quantifier, you can just point to what has that particular property. So here I want to say that X has the property that is required for this X0. So I can just write exists X. So I want to prove that there exists an X0 that has these properties. I say X is that X0. So exists X. But when I say this, then it says, okay, then you needed to show me that there is an X0 that has this property, P of X0. If you say X has that, you have to prove it to me. You have to prove P of X now. Okay, but how do I prove P of X? It's basically part of H here, right? So I can again do total, or I can destruct H and then do assumption. Okay. Okay. We're half done. What do we do for the other side? So here's the thing. I want to prove this entailment. I want to say that if Q and there exists an X such that P of X, then there exists an X such that Q and P of X. So basically I can move the Q inside the quantifier. Okay, how can I do this one? Well, the first thing I do is intro, right? Because I want to get the left-hand side of the implication up there. And then I can do split H. Oops, sorry, destruct H. I always forget this. So now I know that Q exists. And I know that there exists an X in A such that P of X. Okay, so I now destruct H0. Now I have everything that I wanted. I want to show that there exists an X0 such that Q and P of X0. I say that just use X as this X0. So I just say exists X. Okay, it says, okay, so now you have to prove that Q and P of X. But Q and P of X are both assumptions there. So I can just do total at this point. But if I don't want to use total, what else can I do? I can also do split again here. And then Q is an assumption. And then PX is also an assumption. Okay. I have a shorter version of this here as well. It's basically the same ideas, but I will put this on canvas. I'm sure there is also a much shorter proof. So there are actually competitions where people try to write the shortest possible cock proofs. But here's another thing that is interesting. And this is the dual of the Frobenius theorem. And the dual is basically the same as the Frobenius theorem, except that instead of having existential quantifiers, we have universal for all quantifiers. And instead of and, we have or. So basically, this is what it says. It says if for all x's in A, I have Q or P of X, then I have Q or for all x, P of X, and vice versa. Okay. Now, the funny thing is, if you want to prove this one, you cannot do it directly. To prove this one, you will actually need this one, the excluded middle law. So you need to have this axiom, which says that for all P, that is a proposition, P or not P. And by the way, this is how you use axioms. So you can just add an axiom. I added an axiom called EM. And an axiom is just something that we accept without proof. Okay, so in this case, I add this axiom. And then now when I want to use this theorem, so first of all, when I want to prove this theorem, first of all, I want to use the axiom. And the way I did that was pose proof and then the name of the axiom. And then I say simplify it. Okay, let's look here and let's see what we want to prove. What do we have? We have our axiom, which says that for every P, we have P or not P. And then we also have this. We know that for every X that is in set A, I had Q or PX. Okay. And I want to prove Q or for all X in A, PX. Okay. So what do I want to do here? I want to do a casework. What is my casework? I want to say that either Q holds or it doesn't. Either Q is true or it's false. If Q is true, then I want to say, oh, this is trivial. If Q is false, then I want to say because Q or PX held for every X, then PX should hold for every X. That's the gist of the argument that I want to make here. Right? Is everyone following? Some of you are very confused. Okay, I put the recording on Canvas. You can rewatch this part. It's not really that confusing. Okay. So I want to do a casework on Q, basically. If you didn't understand the last part, just understand this part. I want to do a casework on Q. If I want to do a casework on Q and say Q is either true or false, I have to take my axiom, which said that every proposition is either true or false, and I have to instantiate that for Q. So I say take H and replace P with Q. So assert G is H of Q. So now I have Q or not Q. And now I can do my casework. And my casework is destructing this G, basically. And when I destruct it, first it says prove the same thing, assuming Q, and then prove the same thing without Q. So if I want to prove this, and I have the assumption Q, and this is an OR, so I get to choose which side I want to prove. I just say I prove the left side, because I already have it in my assumptions. So I say prove the left side. It tells me prove Q. I say, okay, Q is already an assumption. Now, what if not Q is an assumption? If not Q is an assumption, then I want to prove the right side here, because the left side is basically useless, right? So in this case, I say I prove the right side. Now I have a for all, so I do intro. Okay. Now I want to prove P of X now at this point. Okay. But what do I have here? I have this thing here, which says for every X, I have Q or P of X. So I can specifically do it for this specific X. So I can take H0 and I can instantiate it for this particular X. So I can say assert, and I just give it a new name. Again, I use G. G is H0 of X. Okay, now what do I have here? I have not Q, Q or PX. So this means that PX should hold, right? And that's basically what I have here. So at this point, I have a tautology. At this point, I can just say tauto, and that actually ends the proof. But what if I don't want to use a tautology? If I don't want to use a tautology, so, oh, by the way, this is how you write comments. I can destruct G. So I can say Q or PX. I can say, okay, let's first do the case Q and then do the case PX. But this is now very interesting, finally. I'm 2 minutes over my time, but I got to the point where I wanted.
Oh,
Look at our assumptions. We have Q and we also have not Q. Yes, so we have a contradiction in our assumptions. And if we have a contradiction in our assumptions, from a contradiction, you can prove anything, right? A contradiction implies whatever you want. So if you find a contradiction in your assumptions, you can just write contradiction, and that's it. And that's a valid proof, because you found a contradiction in your assumptions, at least in this particular node of the proof tree. So you can do contradiction. But another thing that you can do is that you can try to eliminate one of your assumptions. So you can say, I want to eliminate H1, which means that I want to use my other assumptions to prove the negation of H1, which is basically the same as finding a contradiction. Okay, so I say I want to eliminate H1. It says, okay, the negation of H1 is Q. Can you prove Q? I say, yes, it's already an assumption. Okay. And then the last remaining part is also a very easy case where you want to prove PX and you already have PX. So that's also an assumption, and QED. And yeah, so that's how you use Coq for proving stuff. We will see much more interesting proofs very soon. Proofs that say that a particular program works correctly. For example, let's say I have a sorting algorithm, and I want to prove that the output of this algorithm is always really sorted. So I have to give a mathematical definition of sorted, and then I have to show that any output of this algorithm satisfies that mathematical definition. And I have to give a proof like this. Okay.
Induction.
Great. Yes, we will have inductive proofs as well.